So once ma'am confirms, I will just write it on discourse, okay?
Yeah.
With the
Okay, sir.
confirmation.
Okay, ma'am. Okay, sir. Okay, sir.
Yeah. Okay. Gaurang, last Saturday we didn't have a meet because you had the NPP, so we preponed the session to Wednesday, right? I took exchanged my session with the TA session and we revised for the NPP. So last Saturday we didn't have any session because you had the NPP, right, for 3-4 days. That's why. Okay, so let me begin. Let me open a PPT.
So
Just
today
one
we'll be
minute.
doing the week 7 or week 8?
Week 7, week 7. We'll do
Okay.
week 7. Okay, first week 7, then week 8. Not today, like today only week 7. Next week we'll do week 8. When is your quiz to? It's on 23rd, I guess, right?
Yeah, next Sunday. Yeah.
Next Sunday. Okay.
Yes, sir.
Okay, then I think we need to do an extra session before that because next Sunday means we only have one more session. That will be the revision session. So we have to do more for week 8. Fine, that is not an issue. We'll schedule that. Okay, just give me 1 minute. There was some issue with my writing device. I'm just connecting it again. Then I'll share the screen. Yeah, I think now it's fine. Okay, just tell me when it's visible. Okay, I've started the screen sharing. If it's visible, just confirm once.
Yeah, sir. It's visible.
Yeah, okay. So see, week 7 and week 8 are related. In fact, all the weeks which you will see now, they are the GenAI weeks, the DL part of the course we have completed. So GenAI basically covers a lot of things, like you have things in language, you have things in speech, you have things in vision, which is basically your images. So I think vision, you guys have a good idea now because you have seen some CNNs and some modern architectures of vision. We can even approach vision with GenAI techniques, which we will be seeing towards the last week of the course. But currently, for the next few weeks, we'll be looking at language. Okay. So from week 7 to around week 10 and 11, we'll be looking at something called as NLP. NLP is a subset of machine learning and GenAI, which is basically on language. It's called as natural language processing. Okay. Now, what happens is the best example, like I don't think I need to give you an intro also because you already know the best example of NLP is what you use, right? So ChatGPT, then Gemini, okay, then I think Perplexity, which is quite free for us now to use. So Perplexity, etc. All these models which are there, these work with natural language processing. Okay, these are called large language models because they are very large in size in terms of parameters and everything. We'll come to that later. Now, what is the core of NLP? The core of NLP is simple. There is a input. Okay, input means what prompt you're going to give, right? This prompt is your input. This prompt can be anything. This can be a question. This can be a statement. This can be a task. Like anything you can write. Right? For ChatGPT, you can write who is the president of India. He'll answer. You can write I am a good person. Just if you write that, then also it'll answer something. You can write a task like do sentiment analysis or solve 2 plus 2. It will give you some output, right? So this prompt can be anything. And then this prompt goes through your model, which is basically the NLP here. This model, which is your GPT and all that. And then this model gives me an output. And this output also is some text, right? So this text can be the answer of the question. This text can be some conversation. This test can be a result of the task, whatever task you have asked. Okay. So the important thing is whenever we are working in the NLP domain, we give text as an input. So this is text. And what we get out is also text. So everything is happening in a text to text framework, right? This is what we call, this is called as a text to text framework because your input is a text, your output is a text. But within this text to text framework, how this output got generated, why some other output did not get generated, why we didn't get a wrong answer, within all that works your NLP model. Okay. This NLP model is nothing but a neural network. It's a very advanced neural network, no doubt. It's called something called as a transformer. You'll see it later. Okay, but it's a neural network. But tell me one thing, neural networks work with a specific type of data. Can you tell me what that data is? Do they work with text? Can you train a neural network on text, like directly on text? Is it possible?
No, it can't
No,
understand
it's
only numbers.
numbers.
It
Just
requires
numbers.
numbers, right? If you remember, even in images, when we studied images, we were not giving the image directly, right? The images were getting converted to numbers with the pixel values, right? So this is what, like suppose this is an image here. I was not training my network with this. I was training my network with something like this, right? Something like this, which was the image, the number representation of the images, right? In the same way, this text which is there, this text also I have to convert into some numbers. There are many ways. We'll be seeing some of them today. Okay. And then these numbers will be pre-processed and processed by a neural network. And with that, we will do the learning. So our task over the next few weeks, that is week 7 to 10 and 11 roughly, we will be studying about how these numbers and how these texts get converted to numbers and how we process them to generate the output, another text. Okay, output is also text. So how do we do that? The entire cycle, and what type of models do we use? They are neural networks, but just like in images you had CNN, right? A specialized form of networks. In here you have some other specialized forms of networks, which we will be studying. Okay, so this is the agenda for the next 4 weeks. I have not taught anything so far. I've just told you what is the overview of what's to come. So any question on this so far?
So like here we actually, is it like here we actually use the text-to-text model. Then what actually the model trains? Because
Yeah, we'll come to that. That's what we'll study today.
okay,
Yes. Okay. The idea is the framework is text to text. Now, how the model actually operates there, that we will be studying now. Okay. Yeah. Anyone else? Yeah, Disha. Yes.
Sir, could you please explain once again?
Okay. So what I was saying is, whenever you work with a NLP task, NLP means language, right? It works with language. So just like ChatGPT, Gemini, which you must have worked with, right? So what happens when you give any input to ChatGPT? It is always text, right? So you will tell, right? Do this task or write a code to sort a
Yes, sir.
recursive linked list, something like that, right? You give a text, right? In the output also, ChatGPT will give you some text, which might be Python code in form of text, right? Which might be some paragraph in form of text or so on. It will always be some text, right? So your input that goes to an NLP task is text. The output that you get is also a text. Within this text-to-text framework, there is a model, which is the NLP model, a neural network which sits, and that model trains on the text and tells you what is the next and actual text to predict. Like for example, if you ask who is the, I'll write in short form, president of India, right? And ChatGPT gives you this. Is this possible? Not possible, right? Because
Yes,
ChatGPT
sir.
knows Donald Trump is not the president of India. But how does ChatGPT know? ChatGPT is not a human. He doesn't know Donald Trump won the election last year and he became the president of US, not of India. So how does ChatGPT do that? Because ChatGPT knows that when this question is asked, this is the answer that it has to generate. That's the idea. How it does, this is quite a complicated thing. If you look at from the high level, we'll decode it slowly. Okay. So our
Okay,
task is,
sir.
how does models here, the model that sits here, which is the neural network, how does it know that with this text, this is the response and this is not the response? That is the question. If I write who is the president of India, it will never respond Donald Trump. It will say our president is Srimati Draupadi Murmu. That whatever the correct answer is, that is what it will tell, right? So how it knows that is through some training, and that training is what is called as NLP. That we will observe. Okay, that's the overview.
Yes, sir.
Okay, so now
So,
we can
sir, I'm
begin.
just curious how these models are trained. I mean, is it training every day? Because the current affair and
Yeah, actually, you know what happens nowadays? Again, this is something we'll see later, but I'll just give you a quick idea of what this is, not the technicality. So initially, we just had LLMs which were trained. Okay, so they had some fixed data and they were trained on that. So obviously, if I have my training done on August 2023 and I get a new president on August 2024, obviously ChatGPT will not know who the new president is because it does not have that data, right? So nowadays, what we have is we have LLMs trained. Basically, the general training is done on some general data so that they know how to converse in the language. Alongside that, we have something called as a technology called as RAG. So RAG means the LLM knows how to generate text that it knows, but alongside that, whatever text is getting updated, whatever is the current affair, that the LLM searches from some tools it has, it scrapes out resources and then it responds with that. So, okay, so we'll see that later on. How it works, I'll explain you in detail that time. But right now, the only point is that LLMs know that they have to retrieve current information, that is through RAG. So
okay,
this
sir.
can be basically, this is the static, right? So static GK, static general knowledge is given by the training, and this is the current affair. Okay.
so what is the full form of that? RAG?
Sir,
Retrieval
what is
augmented general.
RAG?
We'll see that later. Right now, you won't understand what it is. We'll see that in the upcoming weeks. Okay. Because you have to first understand how the training happens, then only we will come to RAG. The idea of RAG is very simple. Like, for example, I have trained the LLM on, for example, English, okay, and general English, okay, class 5th level English, and I ask LLM what is the meaning of the word euphoria. So general LLM will not know that because in class 5 level English you will not learn a word called euphoria, right? So how will the LLM still respond? The LLM will respond because the LLM will search on the internet, scrape some sources, and find what is euphoria's meaning, and it will give you that. That is what RAG is. So when the model is not trained on some data, but it has the knowledge to go and observe some source from the internet and get the answer still for you. That is what is RAG. Okay. We will see how it works. So don't bother with RAG right now. That is going to come up in later weeks. And once you are understanding what LLM is, then RAG will be clear. Okay. We'll not go into details right now because it will be confusing right now. We have to understand the basics first. Yeah, anything else?
No, sir.
Okay, so let's begin with the week 7. This was just an overview. That's not in week. Everything what I told is not in week 7. It will be coming up in the upcoming weeks as well. So let's start with week 7 now. Okay. Now, when we start with week 7, we have understood first of all that the objective is NLP, right? So we have to do a text to text framework. We have to give input text and then we have to get output text. Now, first of all, tell me one thing. You have seen two types of models. One is your ANN and one is your CNN, right? So in the ANN, you have data like this, which is height, right? Weight, BMI. You have data like this, right? So height is 6 feet, weight is 80, BMI 25. Height 5 feet, weight 80, BMI 27. Like this, you see, right? Tables, your feature label pairs, right? This is what you see. XI and YI. This is the data which we see. If you talk about images, you see CNN, you see images, right? So this is image 1, this is image 2, and these images obviously have their pixels, which are trained using a CNN, right? With the filters and everything, which we have seen. When we come to NLP, so NLP model, I'll just write NLP here. The data is very different. The data is text, right? So for example, how are you? My name is Rahul. This is the data we have, right? Can you tell me what is the main difference between these two data and this data? There is one main difference. Of course, this is image, this is text, this is number. That is one difference. But there is one more difference. Can someone tell me what that difference is?
So they are structured in this continuous type things.
Exactly. So the continuous, basically the word, exact word is this data that you see, this data is called as sequential data. Now, why is it called as sequential data? Let's come to the other ones first. If you see, if I see this BMI, no, sorry, not this BMI, if I see the weight of person A, for example, this is person R, this is person Y. Weight of person R is 80. Does the weight of person Y depend on the weight of person R? It does not, right? Because
No,
my
sir.
weight will not depend on your weight. It is independent. It depends on my lifestyle, my height, my food habits, etc. It will not depend on your weight, right? So it's independent. If I have person Z, will his weight be depending on these two or will it be completely independent?
Independent,
Independent,
sir.
right? Same for his height, because obviously a person's weight and height cannot be determined by some other person, right? Every person is unique in their own way, isn't it? If you see images here, suppose this is a cat image. The first image that I put, this is a cat image. Does that mean this image has to be a cat? Is it determining it anywhere? It's not, right? It can be a
No,
dog image
sir.
also. In my data, my first image is a cat. My second image can be a dog as well, right? It can be a cat also. It can be anything. This image being a
Yes, sir.
cat does not tell me that this image has to be something, right? It can be anything. There is no relation here. Data is data. We have no relation, right? But if you see here within the data, I am writing how are you. So when my like the first word is how, second word is are, and third word is you. Do you think the word are depends on the word how? Is it depending?
Yeah, obviously.
It is depending, right? Because
Yes, sir.
are you? If I just said are you, this can be are you stupid? Very different question, right? Just removing the heart, this was a very nice statement. This was a very arrogant statement. Are you stupid? Not a good statement, right? So that means the how word being before are has determined the course of the sentence, right? I write how are and then the next word comes you. Can I write like just think of it like natural English only? Don't think about NLP right now. Just natural English I'm asking. How are Jasmine? Jasmine is a flower. Is this a valid sentence? It's not, right? Because when I have how are, the highest probability of the word that's going to come next is you, because that's how English has been structured. Okay. Then I write my name. After my name, I get this word is. I will not write my name, height, Rahul. Is this valid? Like, is it valid? Not valid, right? My name, height, Rahul. What is the meaning of this? It's not valid. So obviously, I know that if my first two words are my name, the third word has to be is, and the fourth word has to be whatever my name is, right? So what we are seeing is the data which is there. Like for example, if we write, let's just get familiarized with the notation as well. So suppose I have a data which is a sentence. So let's call this let's call it sentence S1. This has four words. Let's say X1, X2, X3, and X4. Four words of a sentence. We know that X2 depends on X1, X3 depends on X2 and X1, because obviously X2 depends on X1, right? So it's a chain that's going. X4 depends on X3, X2, and X1. Is this right? Do we agree with this?
Yes, sir.
We do, right? Yes. Now, obviously, there's one more thing. S4 is there, the fourth word. It might depend on this very much, this very much, this little less. But this depends on this, right? So there is a chain. There is a chain of dependencies which is getting formed, right? So this is called as, commonly, if you see in some book also, it's called as chain of dependencies. So the main difference between normal data and sequence data is sequence data depends on its previous values. Each value in the sequence is conditionally dependent on the previous value. That is the idea. Okay. So whenever I write any sentence or any sequence, sequences can be something else also. It's not that it's just sentence. It can be anything. One more example if I give you for sequence. Like sentence is the most easy example to understand. Like for example, you have stocks. Okay, so I have a stock here. Suppose I bought a stock, okay, S1, and the stock in April valued like suppose 80 rupees. Okay, in May, the company did well, so my stock price rose to 90 rupees. In June, I had some recession, so my stock price was high in May, but in June, because it got hit, it became 85. It's not 80 because in May it was high and my June price is slightly lower. So it's still more than 80, but it became 85. So I can see, right, there is some relation. This price was very high and it did even well, so it rose to this price. This price went down again because this price was high, but there was some recession, so it went down. But it did not go out very much, right? Because the previous price was very high. So the fall was not very sharp. Okay, so this kind of a data is also depending. So this, so let's call it x3. X3 depends on x2. X2 depends on x1, and that is why x3 also depends on x1. Dependency does not need to be very extensive. Even some basic indirect way of dependencies are considered under sequential data, right? So if you remember this type of data, if you have done your MLP course, you'll be remembering this type of data is called as time series data, right? Because time
Yeah,
series means you see it in various time periods. This was April, this was May, and this was June. So this was monthly, right?
these
Monthly.
are these things are only do like this time we are doing this only, sir.
Yeah, yeah. With the practical is time series, yes, of week 8. Yes.
The project, yeah, we're doing this only.
Okay, okay. For MLP project, you are doing time series only. Yeah, yeah, yeah.
Yeah.
Correct. So this is what sequential data is, right? So time data is also sequential. We'll not be dealing with time series very much in this course. Like there is a practical that is given in week 8 on time series to give you an idea of what sequential data is. Our focus will be on text, but just to illustrate, time series is also sequential. So that's why I just gave an example. So I hope now the idea of how the data that we are going to deal with is different from ANNs and CNNs. I hope that much is clear to everyone. So any question on that? Then we can move to the models.
No, sir.
So I think that is the reason why ChatGPT, like if we give some typos or if we deliberately use some wrong grammatical sentence, it auto correct it.
Exactly, because it knows the dependencies, right? The exact dependencies. See, let me tell you one thing very simple. When you train a large language model, like whenever I have taught about LLMs, this is one example I'll give. This is something more relevant for next 2 weeks because right now we are not into LLMs so much. We're just understanding the basics. So when you train a large language model, it is just like training or teaching a class 1 or class 2, a second class or first class child English. A child who's in class 1, who's in class 2, is learning alphabets, then he learns words, then he learns sentences, right? Then he learns paragraphs. That is what training ChatGPT is. You have to make it understand the basics first, then you have to make it understand advanced sequences. Okay, that is what training an LLM is. You will be appreciating this example more in the upcoming weeks when we understand what LLM is. Okay, but we'll come to it again. Okay, so this was the first topic of this week, that is what is sequential data. Now let's try to understand it a little more mathematically, okay, because we have to deal with the mathematics and that's going to be quite important for when we understand the models, right? How the data is modeled mathematically. Okay, so let's go to the mathematics. Let me just change this pen a bit. Okay, so what happens? Very simple. So let's take another sequence. So let's call it S, and this is, again, we'll take the simple one. How are you? Okay, we'll ignore the punctuation for now. We'll just focus on the words. Okay, so when we come to the sequence, how are you? There is something called as time step. Okay, in NLP, you have something called as time step. Time step simply means a counter for the words, basically. So this is time step 1, this is time step 2, this is time step 3. Right? Pretty simple. Just the counters. So if your word has 5 words, if your sentence has 5 words, it has 5 time steps. First word is the first time step, last word is the 5th time step. That's the idea. Now I'll introduce a notation called as probability, the simple probability notation again. I'll write something, just tell me if it's valid. Probability of R given how? Is this valid? Can we compute this?
Yes.
We can,
Yeah.
right? So what is
1 by 3.
conditional, right? Conditional probability. When does
Yeah,
conditional
we can
probability
do.
happen? Like I say, if you remember stats 1, P of A given B means A depends on B, right? If A depends on B, then I can define P of A given B, which is P A of intersection B divided by P of B. This formula had come, right? But if A and B are independent, can you define this then? Is this possible? Sorry, is this possible? of A given B? Can I compute if A and B are independent?
No, no, no.
I
Yeah.
can't, right? Because then what happens? P, A, intersection B, they are independent, so the intersection is 0, right? So this becomes 0. So I can't define this, right? So only when an event A depends on an event B, I can define something called as conditional probability of A given B. So that is why when we talk about sequences, sequences depend, right? This depends on this depends on this depends on this, right? So this is if there is a dependency. So I can compute these conditionals. In the same way, if I see probability of U given R and how, is this possible? Can I compute this?
Yes.
Right, no? Because this is the first one, this is the second one, this is the third one. So it depends. So this is also valid. Can I compute this?
No, sir.
Yeah, because they are not independent. The events are still dependent, but U is not depending on how, right? How is not depending on U, right? U is depending on how. So the sequence is going like this. Okay, so this direction is also very important. So this is called a unidirectional sequence. In future, in the next week, we'll be also seeing bidirectional sequences when this actually will be possible, right? But for this week, we are going to see only the unidirectional sequences where words depend from left to right, right? So the words on the right depend on the words on the left. So the current word depends on previous word. Okay. So now if I want to write a general statement that probability of x is equal to t given probability of x is equal to t minus 1. Can I compute this? T is time step, okay? T means time step.
Yes.
So is this valid? Valid
This is
expression?
valid.
Valid, right? Because time step t means this word depends on t minus 1, it means this word, right? And if I say probability of x5 depends on probability of x4, x3, x2, x1. Again valid, right? Because fifth word depends on
Yes,
fourth,
sir.
third, second, and first. Correct? So valid. These are just different ways of writing the notations. In your slides and all, you'll see these notations. I'm just trying to make you comfortable with this. Okay, that's the only idea. Okay. So whenever we deal with sequence data mathematically, we use conditional probabilities to model them. Okay, that's the idea.
So, sir, in this, how is it? I mean, how should we interpret this probability of x being in the sentence, given that x4, x3, x2, x1 are there?
Yes, are the
Is it?
previous words. So this means my sentence is what? My sentence is x1, x2, x3, x4, x5. This is my sentence. Okay? So just like this. So
Okay, so
how?
the sequence should be there. I mean, we cannot write x3, x4, x2,
No,
x1.
no, you can't write because that dependency is not there, right? If you write x3, x2, because x3 is not depending on x2, right? Sorry, x2 is not depending on x3, right? So you have to
Yes.
have this order. This order, that's why it's called a sequence, right? The order matters.
Yes.
The
Okay.
order matters. Okay, that's the idea. In the next week, we'll see bidirectional sequences where you can even reverse the order. Okay, but right now, let's forget that. Let's just assume order does matter. Order will matter there
Reverse the
also
order,
because you
but
can't
we
do
cannot
arbitrary things by
jump.
order. Yeah,
We cannot mix and match.
you can't mix and match because again, see,
Yes.
how are you doing today is a valid sentence. You doing today, how are? Nothing valid, right? You can't train the model on this sequence, right?
Yes.
That's the idea. Okay, so I hope this mathematics is comfortable. Now let's try to introduce one more notation. So one more notation is I want you to tell me again. I have this simple sentence: how at time step 1, R at time step 2, U at time step 3. Right? Simple question. What is the probability? Suppose this is ChatGPT, right? Suppose this is ChatGPT, and this ChatGPT gives me this output. Okay, ChatGPT is giving me an output. How are you? What is the probability of this whole sequence? Can someone tell me? What is the probability ChatGPT gives me this sequence? How are you?
I think one.
One.
No, not one. Like suppose ChatGPT knows 50 words. Okay, ChatGPT knows 50 words. And out of those 50 words, what is the probability it gives me these three words itself?
3 by 50.
3 by 50?
3/50.
But won't you use conditional probabilities here?
So, but you are telling that after giving this, it will give some results. But like you are asking for, if the how are you is there, it will return that how are
Okay.
you any part of that.
Let's see. Let's assume there are 50 words. Okay, let's try and understand the data first. There are 50 words. Each word has probability. For each word, the probability obviously is 1 by 50, right? Because there are 50 words, unique words. Okay.
So then sampling without replacement. So it will be 1/50 multiplied by 1/49 times 1/48.
Yeah, that is one valid answer. That first you have 1 by 50 words, then how is gone. That becomes 1 by 49. Then it becomes 1 by 48. But if I
But
say
that
that
is,
you can actually repeat the words, then it will be
I
1
know,
by 50.
I know, but here there is a dependency. So that is why we have to look at the, once we say the first word is 1/50, second word we have to see joint distribution between word 1 and word 2 over the entire corpus of 50 words, and then create the conditional probability.
Yes. So basically, we need the conditional, right? In the end, that
Yeah.
is the idea. So
Yeah.
basically, we have to first do the probability consideration and see the we have to compute the conditionals. Exactly, that's the correct answer. So basically, what we need is none of this. We need to first understand what is the probability of how. This is pretty easy, right? So probability of how will be basically 1/50, right? Then we need to multiply this with what is the probability of this word R coming after how, right? Because it's a sequence, right? It's not independent. I'm not doing words like this w1 w2 w3. I'm not generating words like this. W1 happens, then w2 depends on w1, w3 generates, w3 depends on w2, and w3 generates depends on w1. So I have to preserve the sequential ordering here as well. I'm not asking you what is the probability of ChatGPT generating me these three words. That is not the answer. I'm asking you what is the probability it generates this sequence, not some other sequence. That is probability of how. So let me even eliminate the mathematics here. Let me just write it in the equation format. So the probability here is going to be simple. Probability of how into probability of R given how into the probability of U given
You given how and I.
how and
R,
R, right?
comma
So
how.
R and how. Yes. So R and how. Okay. Yeah, how and R. Sorry. Correct. It was how and R. You have to preserve the order, right? So how and R. So first how and then R. Okay. Can we understand this now? Is the idea clear how the generation happens? Everything happens conditionally. First word obviously comes with the randomness because there is no condition here. Second word depends on the first word, so I have to calculate the conditional probability, not the normal probability. And the third word happens based on the second word and the first word together, right? So that is why that again becomes a much more high level conditional probability. That's the idea.
So
Okay.
one observation is if a sentence has 8 words,
Mhm.
then to calculate the probability of 8 words, it has to be conditioned on a sequence of 7 words. So that
Yes. Yes.
computation will be little lot more involved.
Lot more involved, exactly.
Yeah. Yeah.
So to eliminate that, something again we'll see that later, something is called the attention mechanism. That is what is used to eliminate that, because when you like in ChatGPT, it generates, like for example, you said generate 1,000 word essay on global warming. So the 1,000 words depends on all the 999 words before it in that order, right? So to compute that conditional probability, it's very cumbersome. So we have something called as attention mechanism that basically tells GPT focus on these words only of the sequence, and then it computes. Okay, that we'll see later. But currently, we can assume that whenever we are generating words one by one, the current word will always depend on all the previous words, and we have to take conditions. We cannot take random individual probabilities. We have to condition the distribution and then get the final probability. That's the idea. Okay. So this is very important for your quiz also. This formula, that is the conditional formula, is pretty important because they will be asking you questions based on this in the quiz. So our idea will be very simple. Don't go on any formula. The idea is very simple. Current first word normal, second word depends on first word, third word depends on first and second, fourth depends on first, second, third, and so on. Right? So get the conditionals. They'll be given when well and good. Otherwise, you calculate it with probability formulas, and then you can multiply all of them and get the final probability of getting one sequence. That's the idea. So any question on this? Comfortable with this?
Yes, sir.
Okay, great. Something on the chat?
No, no, sir. Actually, it was my error
Okay,
from me.
okay. Yeah, how and R. Yeah, correct. Same order. Yes. Okay, so that was the basic idea. So now that we have understood what conditional probabilities and what sequential modeling is, now we can come to the models, right? So let's come to training. So we have understood what it's going to happen, like what is the output going to look like. So now we can come and understand what training is going to look like, right? So let me insert a new slide and let's talk about training. For training, there are some words we need to understand first, some definitions, because those definitions are something which we'll be using forever, like not only in this course, in the future courses in the degree level, and when you work as well in this field, you will be using those words always, right? So a few words, let's try to understand these words first, and then we'll understand the different things, right? So for training, first of all, the first word is pretty simple, that is the data, and this we already know, this data is the sequence data. Okay, then we have a model. Of course, we have to train a model, right? This model is called the LLM, the large language model. Earlier, it was something called as RNN, which is recurrent neural network, which we will see today. Now we are using LLMs. Okay, we'll explore all of them later. The third word comes out to be corpus. Has anyone heard about what is corpus? Can you tell me what corpus is?
It's like the dictionary collection of
Exactly.
all the
Dictionary,
words.
a large
So
dictionary.
corpus is basically no, it's not exactly the dictionary. There is the dictionary. There is another word for that. It's called the vocabulary. That is the dictionary. Corpus is the entire text. Okay. So basically, when you see data, right, there will be many sentences, right? Which suppose you have 100 sentences. So all these 100 sentences combined is the corpus. Okay, so entire text where model is trained. This is called as corpus. Okay, not very important, but still it's good to know.
So
One
like a
example I can give you.
so the
Yes,
mathematically it's a universal set.
kind of. Not universal, because universal means include everything. This means the text which I'm using for training, but all the text. You can think of it as universal. Yes, that's valid. Example, ChatGPT 2.1. The first ChatGPT, it was trained on no ChatGPT, not one. ChatGPT 2. The second ChatGPT, which I think came in 2023, that was trained on Wikipedia. 8 million Wikipedia pages. Okay, so that 8 million Wikipedia pages will have lots of text, right? So combining the text of all the 8 million pages is the corpus. That's the idea. Okay.
So, sir, in other words,
Sir,
in a dictionary, there could be 2 million words, but the Wikipedia pages, when it's combined, it's only, let's say, 2 million. So only 25%, because there are a lot of words which are very, very rare, like, used in
Yes, yes, it is.
1930s or 40s, not used anymore, right?
Yes,
So,
yes.
so that's the technical difference between corpus and the vocabulary.
Dictionary.
Yeah,
Yeah, yeah.
okay,
Vocabulary, yeah, exactly. That is
got
the
it.
main difference.
Okay, thank you.
Okay. So then, as we have now seen, next is the vocab, which is basically the words we are training on, right? So the word list. So one second, yeah. So the word list on which the model is getting trained, that word list is called the vocab. So for example, like let me maybe show you some example. Like let's go to our Wikipedia page. Okay, so let's do IPL is trending nowadays quite a lot because of some auctions and all. So let's see the IPL Wikipedia page, right? Where is it? Yeah. Now, if I train a model on this entire page, this page becomes my corpus, right? All the things. Let's assume we are training it on this much. So this whole thing becomes my corpus, right? I've trained my IPL model on this data. Now, what is the vocabulary? Vocabulary is just the list of unique words which are there in this corpus. So basically, the becomes a part of the vocabulary. Indian is a part of vocabulary. Premier is vocabulary. League is vocabulary. Professional is vocabulary. Is vocabulary. Is vocabulary. 20 is vocabulary. Everything, right? So these all words become the vocabulary. Corpus means the entire text as a whole. Vocabulary is all the unique words that are present inside the text. That's the idea. Okay. Are we clear now with what is the difference between corpus and vocabulary? Any questions?
no, sir.
Yeah, so these are just some technical terms, so just get used to them, because when you code and all, these terms will be used a lot, right? So that's why it is good to know them.
So in Python terms, if I put a set function on the corpus, I'll get the
Yes, you'll
vocabulary.
get the vocabulary, exactly. So
Yeah,
I'll just write it here. That's a very good example. So you just use set corpus and you get vocab. Yes. Again, see, vocabulary right now for this week 7 and 8, we will be using vocabulary as the word list. There are actually other methods of generating vocabulary as well. There are 3 methods. Let me just write it here, but we'll not go into them. One is called as the character vocabulary, and one is called as subword. All the models which we have, they use this as the vocabulary method, subword. So what happens is, just an example, like suppose there are 2 words, right? Study and studying, right? So these are 2 words. So if I have vocabulary as my word list, this becomes one part of the vocabulary, this becomes another part of the vocabulary. What happens in subword is, it will take study as one subword, it will take ing as the other subword, right? The advantage of this is study will be there. So any word which has study, studying, studies, the study will get separated from them as a word. And any word which has ing. So ing can be here as well, right? Playing. Ing can be working. So everywhere this ing will get separated into one vocabulary. We'll see that actually helps in reducing the size, because if your vocabulary is too large, again, your model becomes very expensive, right? The training is very difficult. Okay. So that is why when we are working with vocabulary, the idea of using subwords as a vocabulary method is very famous. I think in this course, we are not going to focus on that much. So for this course, you can just remember vocabulary is a list of unique words which your model has, which your data has. Okay. All right. Now,
Okay, sir.
yes. So there is one problem, small problem with this. We know that vocabulary is the words which we will be using to train the model, right? So these will go into the model for training. So this is the same problem which I was talking about in the beginning of the session. We cannot train a model on words, right? Because your model is a mathematical equation. Your model is what? This is a model, wx plus b. Is there any word here? These are all vectors, right? Vectors and matrices. There is no word inside this. So how will you train a model based on these words? How is it possible?
Encoding.
Yes. So we have to convert these into numbers, right? So convert into vectors, basically. That's a better word. Convert into numbers or vectors. That's the idea, right? Now, to convert words into vectors, there are 2 ways of doing it. One way we'll be seeing right now, the other way we'll be seeing in week 9. Okay. So the first way is simple encoding. Again, MLP people will be knowing this. Have you heard about one-hot encoding?
Yes, we did.
Yes,
One
sir.
zero.
Yes,
Bunch
yes.
of one
See what
zeros.
this
Yes.
means is, suppose we have 2 words in the vocabulary or 3 words. Apple.
So we create a 3 space matrix.
Yes, you get a 3-space matrix. Apple gets a 1 here, mango gets a 1 here, and guava gets a 1 here. So if I have this is my sentence now. So what is my sentence? My sentence is guava, guava, apple.
Apple.
Right? Simple method. So it's basically whatever your vocabulary is, that size of a matrix you create. For every word, they will have the 1 at a specific index and zeros will be there in all other indexes. Right? So can you tell me, suppose my vocab has M words. What will be the size of the embeddings here? One-hot encoding embeddings. What will be the size? M cross M, right?
M cross
M
M.
cross M, yeah,
Yeah,
M
M
cross
cross.
M.
Because I will create m-dimensional vector and m times for all the words. So m cross m is my dimension of the one-hot encoding matrix. Any problem with this? Is it bad to have m cross m?
Yes, because there are a lot of words.
Yes.
Yeah, so the small IPL Wikipedia page that you saw, that contains at least 200 words, at least. And now I'm telling you, you have trained your ChatGPT on 8 billion Wikipedia pages. So how many words will be there? Millions of words, right? So that means the matrix is going to be huge, like this. Massive matrix. That is a problem.
Millions plus million.
Okay.
Yeah.
So let me write it on a separate slide. You can use it as reference later as well. So the first problem, so limitations of one-hot encoding. First is size, that is m cross m. Right. So as my vocabulary expands, this matrix becomes extremely big, and that is very computationally heavy. Right. The second thing is, have you heard about this word? Sparsity. What does sparsity mean?
Like many unknown, like with same values of
Yeah, and
same
that is
column.
basically zeros, right? So
Yeah.
it becomes number of zeros. Now what happens is, for all these embeddings, if you see, these zeros don't make any difference, right? I am interested in where the one is. So the one is here, one is here, and one is here. Wherever the zeros are, I don't give any attention to that, right? Because that doesn't matter. My attention is only to the ones, right? So what are these zeros? These zeros are just wasting the space, right? So they are just waste of space, right? And if you see one-hot encoding, on every row, one number will be 1 and every other number will be 0, right? So if I have a
Yes, sir.
matrix which is going to be million cross million for million words, I will have one word at every row, which is 1, and then you will have million is what, 10 lakh, right? So 9,99,999 words will be zeros, right? At every row, everything is going to be 0 and one word is going to be 1. So I'm going to have like almost 99% sparsity, isn't it? Filled with zeros,
Noise.
which are
Full
of
of
no
noise.
use. So I'm wasting my space. I'm still storing them, because otherwise, if I don't store the zeros, my one-hot encoding doesn't make any sense, right? So I have to store the zeros. And once storing them, they are not giving me any advantage, but they are consuming a huge amount of space, which is unnecessary. Huge amount of GPU, which is unnecessary, right? That's bad. There is a lot of sparsity, which leads to a lot of waste of space. Okay. These are the two main compute-based reasons. There is one more very important reason, and that reason is the semantic reason. Semantic means language-oriented. Okay, that semanticism means study of language. Okay. Tell me one thing. Apple, mango, and guava. These are okay. Let me take a new slide. Okay. So suppose my vocabulary now is, I'll take a new vocabulary and illustrate this example. So my vocabulary is I love apple. So my one-hot encoding is what? I will be this. Love will be this, and apple will be this, right? Can you tell me just numerically, if you look at this vector, and this vector, aren't they same? Like if you compare them with any way, the what is them like vectors? There are some things you use for comparing vectors, right? Like magnitude of vector. Aren't the magnitude same? One for every vector,
Yeah, same.
right? This is one.
Yes, sir.
This is one. This is one. The other one can be, let's say, distance. Can you compute the Euclidean distance between them? Aren't they same again?
Same, yeah.
Root 2, right? Because 1 square plus 1 square, 2 square and square root of that. Root 2 for this, root 2 for this, root 2 for this. Right? Let's compute Manhattan distance. Manhattan is the mod of x minus y. 1 for this, 1 for this, 1 for this. Sorry, 2 for this, 2 for each, right? 2 for this, 2 for this, 2 for this. Same, right? There is no difference in distance. But now if you see logically, semantically, I is what? I is a pronoun, right? It refers to a human. This refers to a human, which is you. Love is an emotion, right? Apple is a fruit. Ideally, the number should be different, right? For these, because I need to tell my model, right? Differentiate between a person, an emotion, and a fruit. If I feed my model these embeddings, the model will realize person is same as emotion is same as fruit. It is not, right? Are you getting it? So if I take one-hot encoding, the model does not understand the differences between the words. It knows that my fruit is going to have a one here, my love is going to have a one here, but it does not understand that love is an emotion, apple is a fruit, right? If I talk about hate, another word, hate here, and let's say there are 4 embeddings now, this is going to be like this, right? Let me add one more 0 to each of them. So my hates embedding will be like this, right? Again, if you see love and hate now, so if you see love here, and sorry, let me just minimize this. Yeah, if you see love and hate, love's embedding is looking like this, and hate's embedding is looking like this. They are same again, right? The distance is same, the magnitude is same, but it should not be, right? Love and hate are very different emotions. And if I look at one more, say like, and like is looking like this. If you see the distance between love and like, which are good words, similar words, and the distance between love and hate, which are very dissimilar words, distance is same, root 2, both of them, isn't it? Distance between love and hate, which are very different words, and distance between love and like, which are very similar words, distance is the same. So my model is not able to understand what is actually the difference, which words are similar, which words are different. That grouping that you need to know to understand language, model is not understanding that, right? With one-hot encoding. It is this understanding that each word will have a one different way, but there is no difference or similarity between any words. So the idea is there is no semantic learning. The crux of a language, which is semanticism, this semantic learning is absent between one-hot encoding. That's the idea. Can we agree to this now? Any question on this?
No, sir.
Right?
So like it cannot capture the more specific features like
Yeah.
yeah, that
The
was the problem.
relations, the language you construct, the similarities, it does not capture that, right? So on a one-hot encoding perspective, basically I can just add a statement and you can just tell me whether it's correct or wrong. On a one-hot encoding perspective, the distance between similar words and the distance between opposite words, same, right? No difference. Distance is always same. You take any one-hot encoding and you compute the distance, you will find the distance is always same, which is root 2.
Yeah, mathematical no relationship.
No relationship. So no relationship. No semantic relationship. It does not understand anything, right? That's the idea. So whenever we talk about one-hot encoding, the main disadvantage is the model does not learn any relationship between words. It treats all the words in the same way. It does not respect similar words. It does not disrespect different words. It treats them all one and the same. That's the idea. Okay. So once you understand this idea, this will help you to understand why we don't use one-hot encoding as our primary encoding technique. We use something else.
So we can use the label encoder or the ordinal encoder also.
Again, if you use that, you won't find many differences still, right? Because if you use a label encoder, let's say, so what happens in label encoder? Let's say there are 2 labels, 3 labels: boy, girl, man. This becomes 1, this becomes 2, this becomes 3. And suppose let's say woman, and let's say grandpa. Okay. Again, the equation is same, right? These values it gets. Distance between boy and man is distance between 1 and 3. Distance between girl and woman is distance between 2 and 4. But distance between boy and grandpa is distance between 1 and 5, which is big, right? A boy, when he becomes old, he becomes a grandfather. So the distance between these two words, which are denoting boy and grandpa, is very large. But on the other hand, distance between woman and grandpa, very small, right? 4 and 5, just 1. Whereas woman can never become a grandfather, right? That's the idea. A grandfather can only be associated with the male words, not with female words. But here my grandpa is getting 5 and woman is getting 4. It is close, whereas boy is getting 1, much farther, right? So no advantage. I'm still not able to capture any relationship between them, isn't it?
Yeah, it's true. Yeah, understood.
Yes. So what happens is the solution to this, we'll be seeing the solution later. It's not in the scope of this week, but I'll just tell you what the solution is. The solution to this is you use the one.
It's like I know the build. It's a vector embedding or what?
Yeah, we do vector embedding, but the actual solution is, if you remember from week 2, there was one term that we had studied in week 2, which was called as This. Can someone tell me what this is?
Universal approximation.
Yes. And what does this theorem say? If you
Right.
use a neural network, you can learn anything, right? Basically, training a deep neural network can solve any problem in the real world. That's the idea. And that is what the solution is for this as well. So what happens is we train the embeddings. So we train a neural network, and with that neural network, we train the embeddings and we learn them. And what do you mean by learning the embeddings? You will find some embedding values here, here, and here. But what this method does is it gives similar values to the similar embeddings and it gives different values to different embeddings. So the distance between boy and man is going to be much less than the distance between boy and girl. Right? So it is now appreciating that boy and man are similar words, whereas boy and girl or man and girl are different words. Okay. So now how does this happen? We will see later, not right now, but this is the idea. So just remember, whenever you want to train a machine on something and your machine is stuck and it's not able to learn, the solution is build a deep network. When you build a deep neural network, anything that is there, because of this UAT, anything that is there will be learned. And that is what the inspiration came to train the embeddings. We take a separate network and we train the embeddings first, and then we feed those embeddings to our language model to learn the language. That's the idea. Okay, how the training is done, we will see later. There is a model called as CBOW. Okay, this we will see in week 9, not right now. This is what is used to train the embeddings. Okay, it's just a network. For now, you can just remember it has the hidden layer, forward layer, your activation function, and those things. Same thing. Okay.
So like you are telling that to get the like to feed the input, we use like any neural network for the like the data pre-processing. You are telling that.
Yes, for pre-processing, this is the first time now. For pre-processing, also we are using a network. For modeling, though, of course, we'll be using a network, the RNN and the transformer. But even for pre-processing, we are using a network now. Okay. So for language modeling, we have two networks. One is the pre-processing network, which will give me the embeddings, and one is the language model, which will basically learn the language and give me the output and so on, which we talked about in the beginning. Okay.
The first one was pre-processing. Could you please repeat that?
No, I'm saying for a neural network, for language models, you have two networks now, right? One is the pre-processing network, which will basically give you the embeddings for the words, convert the words into numbers, and then you have the real model, which will basically learn the language, give you the output, do sentiment analysis, and those kind of tasks, right? That's what I'm saying. But even for
Yes.
pre-processing, earlier you used to in MLB, what did you do? You used to convert the words into vectors with one-hot encoding, right? But now we are actually converting the word to vector also using the neural network so that the embeddings which it learns are actually good. Okay, that's the idea. So if you
Yes, sir.
remember MLP, you did one-hot encoding and then you did the logistic regression and so on, right? That was the actual model. Now you will
Yes, sir.
do embedding model, which is the CBOW, which we'll see later. Then you will do the network, which is basically the GPT, right? The transformer or the RNN and so on. So two models. One is for pre-processing, that is to convert the word into the embedding, and the second one is to get the results from the embedding, right? Doing the NLP task after that. Okay.
Yes, sir.
Yeah, so that is quite a bit that we have understood so far. This was the main part of week 8. Then we have a bit on RNNs, which we'll talk about. But any questions so far on this? Any doubt on this? Is it clear? Good
So
to
like
go?
the model, so the model GPTs and all like now also work on this pattern only.
Yes, the embedding model is there, and then you have a LLM, right? The large language model, which is the main model to learn it.
The transformer.
Transformer, exactly.
Okay.
See, in Transformer, what happened initially, before Transformer, there was a model category called as encoder decoder models. So they had the embedding model first and then the Transformer. And the actual Transformer, what happened is they integrated the embedding model inside the Transformer itself. So both the things happen. First, it converts and then it even models. So both the things happen in the same model. Okay, but it does. The embedding still gets generated, but now both the things, it is a 2-in-1 thing. Buy one, get one type. Right? Both the things happen in one model instead. First, the model generates the embeddings, then the model in itself uses the embeddings and generates the outputs by doing the training. Okay.
So like then this ChatGPT and all must have the access of every websites and all.
Yeah, it does. It does.
So but like can we do this manually? Like can I scrape a government website and all?
No. In each website there are scraping permissions that are there. So in whatever
Okay.
websites the scraping permissions are there, that ChatGPT can scrape. Whatever websites don't have those permissions, that it cannot scrape. Otherwise, that becomes a data breach, right?
Okay.
So
Understood.
like there is a government website on say health data, so that is sensitive, right? You can't leak anyone's medical information. It's that it can't scrape. It'll get blocked. Okay, so it's on contract. I think there's some licenses that they take as well, so it's based on that. It's very well encrypted. But whatever prompt you are giving, that will be scraped, right? ChatGPT gets that and it updates itself with those prompts. So that's why they say don't ever share any sensitive data like passwords, bank accounts on ChatGPT, right? Because it gets an excess of those. Okay. Yeah. So any other question on this?
No, sir.
Okay. So I think we are good to go. So okay, let's take a 2-minute break then we will talk about RNNs, right? Because I think we have had a long session and these topics are quite new as well. So let's take a break for not to like this 1-minute break and then we can start with RNNs after that, right?
Okay, sir.
Yeah,
Okay.
okay. Okay, then we'll meet at 8:55. Okay, so I have actually taken a diagram of RNN because it will be easier to use a diagram rather than draw it. Okay, so what happens in RNN? So RNNs are called as recurrent neural networks. Okay, recurrent neural networks. What happens is RNNs work on a very simple fundamental. You give it x1, it will give you x2. You give it x1 comma x2, it will give you xc. So basically the sequence modeling, right, which we talked about earlier. You will give some word, RNN will predict whatever is the next word. That's how it works. Okay. Then you give the first two words, RNN will predict what is the next word after that. That's the only idea. Okay. So let's try to understand what is the actual structure of an RNN. For an RNN, you have three layers. Okay, so these are three layers of RNN. This one, and this one. This layer is the input layer. Okay, and we call it the embedding layer. Okay, now why it's called the embedding layer, I'll explain you. This is the simple hidden layer, and this is the output layer. Okay, how does it happen? So let's take an example of a 3-word sentence. Let's say again, how are you, right? So whenever we pass the words to our RNNs, initially they did the one-hot encoding, right? So how are you got passed like this, right? And then of course they found out that one-hot encoding is useless. It will not give any advantages. So they basically replaced it with something called as the embedding layer. Now what happens in the embedding layer? As I told you, embedding means you have to train the embedding using a neural network, right? So even in RNNs, they added the embedding part itself inside the RNN directly. So what happened is here you supply the word. So for example, you give the word how here, and RNN with the embedding neural network, it converts it into some embedding, right? So like for example, this becomes the embedding for how, right? Any random embedding, whatever the network will think, some random values will get assigned and you get the embedding for the word how inside this, right? Similarly, when you pass the word R here, you will again get some embeddings which might be like so on, right? This same logic, any random network will be there. It will train the embeddings, make similar words similar, different words different, and it will generate some values here. That's what the embedding layer does, right? It's very simple. Then what happens is, after the embedding layer, you have the two layers, hidden layer, of course, which any network has to do the learnings, and then you have the output layer to predict. Now let's try to understand how this is actually different from the normal network, right? So if you see, in the normal neural network, if I'll just draw it here and maybe I'll ask you only to do the comparison. This is the input layer, this is the hidden layer, this is the output layer. Can you tell me, in this network, do I complete one layer entirely and then go to the next layer, or do I again come back to the first layer, then go to the next, then come back to the first, then go to the next, and so on? What's the process in a forward pass?
Sequential process.
Yeah, so I will first complete the entire input, then I'll go to hidden, then I'll do those wx plus b's here, and then I'll go to output. So it's one when inputs get completed entirely, I go to hidden. When hidden gets completed entirely, then I go to output. That's the sequence, right? But the problem here is in RNNs, what you want? You give the input as how, you want the RNN to predict this word R, then again you give the RNN the input as word how and R, and you want it to predict U. So can you actually finish the entire input and then go to hidden? Is it possible here?
Never.
No.
Never possible, right? Because your
No,
entire
sir.
sequence is not the input. You will give it some words and it will generate the text after that, right? So you don't even have the entire input. So how will you give it entirely, right? It's not possible. So how RNN works is RNN works in a recurrent way. That's why it's called recurrent, because it repeats the same thing again and again. You'll give it some input, it'll go to hidden, you get an output. In the next layer, you take this input plus this one because you give an entire sequence, right? And then you put it here, you get an output. Then you take this one, you give it here, you get an output, and so on. So you do a same thing, recurrence. What does recurrence mean? Repeating the same thing, right? So RNN means you repeat the same cycle again and again with different input-output pairs. That's the idea. So again, let's take a diagram, take this diagram to the next page, and let's see how the entire thing happens, right? So I'll just copy this diagram and we'll go to the next slide. So again, the sequence is how are you? So what happens is I'll start with something, okay? And I'll start with the first word. I think it became a little hazy. Let me do it like this. Yeah. So I'll start with the first word, which I have. I give the RN my first word, which is how. So firstly, it went to the embedding layer. So let's call it EL, and it generated some vector, right, for the word how. Then it went to hidden layer. Hidden layer is what? WX plus B. Same logic is happening here as well. It has some neurons. You do WX plus B. And then you go to the output layer. Inside the output layer, now what you have is, okay, what is the output layer meaning? I have some vocab, right? As I told you, to train a language model, I'll have some vocabulary. Let's say the vocabulary is M words, right? What do you think the output is going to do? What is going to come out in the output?
It's the next word of the sequence.
Next
Yeah,
word of the
okay.
sequence, right? So suppose this is T1, I want T2, right, in my output. That's why I put T2. And where will the T2 come from? It will come from this vocabulary, right?
Yeah.
Yes, sir.
Yes. So this is going to be
Sir, is it the diagram for many-to-many architecture?
kind of. Yes, it's a many to many because you have multiple inputs at every step and then multiple outputs, right, at every step. So kind of.
Okay.
Yes. Okay. Now, can you tell me? I have M words in my vocabulary. One word is how, and I need to tell which is the next possible word, most possible word after the word how. How do you think the model will generate this? Remember the sequence learning formula, right? What do you think will come from there? Generate this.
So I
It's the
think
probability of each.
Yes, exactly. So I'll basically do probability of each word given how, right? And I'll take the maximum, whichever word has highest probability after coming after how is my output word, right? So can you tell me what function can help you do this kind of a thing in terms of neural networks? There are activation functions, right? Which
softmax.
simple, right? Softmax. So in my output, we have a softmax. And softmax over what? Softmax over the entire vocabulary, right? Because we will apply a softmax over the entire vocabulary and we'll see a distribution. And whichever word has the highest probability distribution after the word how, that is my next word, right? So that is why in the hidden layer, we have softmax. Now I have done how and I got this word R, right? That's my most probable word. In the next time step, I will pass this word R and I will also pass the word how, right? Because I have to pass the entire sequence. So I will pass the word how, that is why we have an arrow here. And I will pass the word R, which is the previous one. Now the hidden layer will do some calculations on both of them and then I will get something new here. So what will this be? This will be softmax of the vocabulary over how and R, right? Because I have a how and R sequence which is already there. Then I will do a softmax over the entire vocabulary of which word is the highest probability after this how and R, and that is my next word. Can we agree to this? We can, right?
Yes, sir.
What about the next one? Can you tell me the input to this next layer after this? Let's say the sentence is how are you doing? We have another word. So what do you think is the input to X3?
It should be the
You,
words
how
before
are you?
also.
Yeah, so basically this
How
U,
are
which is
you?
the X2, this comes out here, it goes here, and from here I get both of these, right? How and R, right? So I got the previous time hidden, which is how and R, and I got the previous output, which is U, and now I was what? Here will be softmax of vocabulary again, and over
Against
how
how are you?
are you, right? So what it's going to do, it's going to see the probabilities of all the words of given the sequence how are you. With the softmax it's going to get the probabilities and then obviously it will take the maximum, right? Whichever word has the maximum probability, that will be my word which I'm using at every time step. Okay, So in this way, again, now with this, again, I'll pass an input here. I'll pass all the previous ones here. Again, I'll do a softmax and I'll keep doing it until and unless I want to stop, right? How do you stop? You tell, right? ChatGPT generate a 50-word sequence. If you don't tell, then there are default parameters that ChatGPT will use and it will generate the sequence till the end, right? So there'll be some ending, some endpoint is there. How that endpoint is determined, that's not important right now. There'll be some endpoint. Whenever I say the endpoint has been reached, that point will stop the cycle. But until and unless the endpoint is reached, we'll keep generating the next word with this cycle. What's the cycle? You have an embedding, you give a word, you get an embedding, then some hidden layer does the calculations, then you do a softmax over the vocabulary over the current sequence. You pass this output, you pass the previous word, that is the input to the next layer. Again, you do the hidden layer, then softmax. Again, you pass entire things to the next layer, hidden softmax, and the cycle continues. Okay, and that is how you generate a sequence, which is the most probable sequence, which we have already seen in the earlier slides. Okay, so this is the forward pass. Okay, this is the forward pass of RNN.
So like the for this like the like the per step, so it must like it will depend upon the either the parameters or the or the vocab, like what is stored on that this iteration.
Vocab. It depends on the vocab. Okay. Are you clear with this forward pass? If you're clear with this, then understanding NLP will be very
Yes, sir.
easy. Clear, right?
Yes, sir.
Simple.
Yes, sir.
Whatever
Yes, sir.
was earlier, the output of the previous layer and whatever inputs were there in the all the other layers will be used. I'll do some hidden layer. Hidden layer will only do the WX plus B's, right? Those calculations. And in the output, I do a softmax, get the most probable word, continue. That's what is happening, right? And why it's called recurrent? Because I'm doing the same thing, right? I'm just providing the previous input. I'm doing hidden. I'm doing softmax. Same thing I'm repeating with different words at every step, right? That's why it's called a recurrent neural network. So these connections that you see, these again, let me again take the diagram to the next page. These connections, that's how the name came. If you see these arrows here, these arrows means whatever is there earlier, you pass that to the next one, right? These connections are called as recurrent connections. This means what? You pass all the previous inputs to the current input. That's the idea. Okay, and this is something which we have seen. Right? That's the RNN. Now, can you tell me the loss? If you have a softmax function, what's the loss that we use with this? Cross entropy, right? We have seen this before, right? Whenever we are doing classification, we are doing softmax, we use cross entropy loss, which is basically in short form, this is this one, right? This loss. Can I use cross entropy here? Is it valid if I can use this? I can, right? Because basically what is happening, cross entropy is used for classification, right? So suppose you have labels, two labels, boy and girl. If my label is correct, then the cross entropy will give me a small value. If my label is wrong, then cross entropy will give me a large value, right? If you see at every time step, when you do a softmax, you have the entire vocabulary as a label, right? All the words are labels, which is the correct word, which is whichever is the most probable word, right? That is my correct label. So I can do a cross entropy. It will be a big cross entropy, but I can do that, right? Still, my cross entropy will still work. But the only difference is in ANNs, which you have like this, you have the loss only once, right? Once you have computed the entire forward pass, you have to compute the cross entropy loss and then you do the back pass, right? But the problem here will be you have to predict the word at every step, right? Every time step. At T1 also you have to predict, T2 you have to predict, T3, Tn. So you have to actually take cross entropy at every time step. CL1, CL2, CL3, CLN, right? Because at every time step there is a classification that's happening, which is the correct word after the current sequence, right? So at all these time steps, you have to take cross entropy loss and you have to see what loss is happening. Okay? Is the idea clear that we have to compute the cross entropy at every time step?
Yes, sir.
Yeah. So what will be the total loss then? If this is the cross entropy of time step 1, this is the loss of time step 2, the second word, third word, this is the loss, and the third, this is the loss. What is the total loss? The total loss of the RNN, there are two ways of defining it. That will be given to you. If a question is asked, you will be given what way you have to use. So total RNN loss. For ANN, there was only one loss, right? So that is very easy to compute. Total RNN loss will be either the sum, which is basically CL1 plus CL2 till CNN, or you can take the average. Okay, both the ways are used. Whatever has to be used in the exam will be given, right? So this will be summation of 1 to n CLI divided by n, right? The average. So either you add up all the cross entropies of every time step, or you just take an average of the cross entropies of every time step, and that becomes the loss of the RNN. So if I ask you what's the loss of your RNN at this time, what is the loss of the RNN network? It will be a sum or the average of the cross entropies. That's the idea. Okay.
So yeah, it's fine. I know we are taking the sum and all that, but intuitively we know if our first word prediction is wrong or second word in the beginning part, then I'm kind of deviating too much, right, from the ideal answer.
Exactly. Because that is the main problem. When we have sequence modeling, my second word depends on the first word. In case my second word is wrong, then third depends on second, fourth depends on second and third. Everything will be wrong.
Right.
Right?
So
There'll be a
so
sequential thing. So my
so
loss
so
will be very large in that case.
so in that case, why are we taking a linear sum? We should be probably taking a weighted sum. Like we should give more weightage to CL1. I'm just thinking,
No,
think
that is
that
that
long.
is right. That is right. Because CL1, if you say we can say CL, if CL1 is wrong, all subsequent CLs are going to be wrong. That is very valid. We should
Yeah.
take a weighted sum. So this is the PyTorch convention. When you do PyTorch coding, the loss comes like this. But your point is very valid. We should take a weighted loss because this is the most important one in both the cases. If this is wrong, everything is wrong after this.
So because we have done some practical, like we are analyzing some NLP, we are
Yes.
analyzing emails to classify, let's say, service tickets, right? So
Mhm.
customer can write about a card or can be reward points, blah blah blah, and then after that there is subcategory because many of these businesses use these automatic email classification systems, right? If you
Yes.
make a mistake in the first model, then the second model you're in the wrong territory, right? So now that is between when you're doing a practical problem solving. Here, you take the first misstep. Like I'm going to Delhi from Calcutta. I took a left turn. You end up in Chennai. There's no way you can recover, right? So that's the whole idea.
Correct.
Yeah.
Exactly. The first word is the main one. If you are making a mistake in the initial, like this is just like if you remember in the initial, like one example from our degree only, in the initial MLP OPPs, we had pre-processing where one question determined the data for the next question. If you make a mistake in the first question, all the questions go wrong after that. So that's just like that. If you make
Let's
a
not.
first, yeah,
Let's not remind those horrible days. I think we are.
okay. Yeah, I can understand. So that's why we have changed the pattern a bit now, so that chain reaction doesn't happen. Yeah. Okay.
Here, what is H naught?
H naught is just some initial hidden layer weight, the initialization. Because if you see, remember on net ANN, you initialize some weights, right, in the beginning, randomly. The H naught just means initializing the initial hidden weights. So if you see ANN like this, so these weights which are the W1 and W2, before I do backpropagation, I'll do some initial weight, right? PyTorch automatically assigns some weight to it.
Okay.
Like for example, 0.11,
Okay.
then
Eventually, H
0.1.
naught will converge to their value where the losses are less.
Yes, exactly. Now then with backprop, this will get converged and in the end maybe you get this 0.7 and 0.6. This is the ideal value, right? Whether you have the minimum loss. Say loss is 0.01 with this. That's why we do backprop, right? To adjust the weights with gradient descent or atom and something, and that will help us to get the better and optimal weights. Same thing here as well. So H0 is just initialization. Okay? This is the initial weights. Because hidden layer, this H1 which is there, this is just an ANN only. It has some hidden neurons like this. Okay. So it's just an ANN which will do the matrix multiplications and everything. Okay, so these are just hidden layers. So the initialization of these weights is what is H0, initial weights. Okay, that's how we write it. Actually, you can even ignore this. It's just the way of notation of initial weights.
So are the RNA and the transformers are like almost same or they are very different?
RNN actually has a problem, a huge problem. That is why that problem we'll not talk about right now, but maybe I'll give you an introduction of what it is. So based on that, transformers use the same logic, but they have improved and improvised to solve that problem. Actually, that's the use. Okay. So, and RNNs cannot be actually used for the complex NLP tasks. So, because they go one by one, right? So, suppose I do a question answer. What happens in question answer? You supply the entire question, right? And then the answer can come one by one words, right? But the question cannot be one by one, right? I have to give the entire question. That's my input. So, RNN cannot understand that kind of a data. It will only be able to generate the data one by one. So, to understand entire prompts and long text, RNNs will fail. So, for that, you have transformers that help you to sort that data out. Okay.
Like the input layer, I think by your words, I think the input layer changes.
Input layer will also change, hiddens remain little same, and there is something different as well called as the attention mechanism that is not there in RNN. In transformer, we have that. Like, what is attention mechanism? Just a hunch today. We'll not again go to the details. Like, for example, you have uh, the animal was scared because it got dark. Okay. So tell me one thing. This it. What is it here? Is it talking about a time? It got dark, it's a dark night, or is it talking about the animal?
The animal.
The animal, right? No, not the animal, right? The time.
Oh,
The
sorry.
animal did not
It
get
got
dark, right? The time
Yeah,
got dark.
time.
The day
Yeah.
became, the night came, right? So we are not talking about the animal, we're talking about a time here. But what happens is when you treat it in an RNN sentence like this, it can get confused whether this it means the animal, whether it means the dark, whether it means because or anything. It does not understand where to pay attention to. It actually needs to pay attention to that this it is actually talking about this darkness, right? Not about the animal. Again, another example. The animal is thin because it doesn't eat. Now, what is the it here? This is the animal, right? Because we talk about eating of the animal, right? So the animal does not eat. That means this it becomes the animal. It does not eat. It means the animal. We're talking about animal here, right? So we need to tell the model that in this it you have to actually pay attention to the animal. In this it you have to actually pay attention to the dark, not the animal, right? There's a difference. This is what the attention mechanism does. Attention mechanism tells which word should focus on which word to even further strengthen the idea of sequences and relations. Okay, that's what attention is. So RNNs have no mechanism. That like you can even see from this structure, there is no mechanism of paying importances, right? Which word is important, which is not. They just generate the word one by one with the sequence modeling objective, right? With transformers, what we have is we incorporate this attention mechanism, and this has actually brought the revolutions of ChatGPT, the invention of the attention mechanism, right? We'll see that later, but this is the main difference. Okay. Okay, so that was about the RNN.
So,
Backprop and all you can like just go through from the lecture. It's not important. The idea is same, right? You have the Adam optimizer and all that we have already seen. So there's nothing different in that.
sir, could you please explain next slide once again?
Which slide? This one?
Sir, 19.
This one?
Yes, sir.
Yeah, so this one I was saying is if you see RNN, you are actually computing cross entropy losses at every time step, right? In the first word, you did a softmax, so there became a cross entropy. In the second word, there became a cross entropy. In the third word, there was a cross entropy. So, what is the actual loss of the RNN? If I ask you what's the loss of the RNN, in case of ANN, you just have one cross entropy, right? Which is at the end, this last one. That's the loss of the ANN. So, the loss of the RNN can be measured in two ways. One is you sum up all the cross entropies of these ones. So, you sum up all the losses of all the time step. That is one way. The other one is you just take an average, right? So that is CL1 plus CL2 plus CL3 by 3. That is the average, right? So that becomes the total loss of the RNN. So if we want to judge the entire performance of the RNN, we have to take into consideration all the losses of all the time steps. That's the idea. Okay?
Yes, sir.
How
Yes.
the theory and then the structure of RNN is to be correlated. In theory, we talk about probabilities, right? But the structure of RNN, it's all weights only. You have weights for your hidden layer.
Actually,
You have
yeah,
weights for your
actually,
input layer.
the weights which are there, the weights are for all the words which are there, they're embeddings, right? You get vectors of the words. The embeddings of this word get transferred here.
No,
The
it's
embeddings
very
of this
clear.
word,
This is clear. This is
yes,
clear. The structure is clear. The weights are getting learnt. But
yes,
the theory, what we are learning for RNN is the probability of the word T given T minus 1, right? This
yes,
is what
yes.
we are trying to say.
PT given T minus 1, right?
But how the RNN ensures the weight where what it learns is based on this.
No, actually, what happens is, like, suppose,
Based on this theoretical aspect, what we are
yeah, I got your question.
learning.
So, what happens is, for example, we gave this word how and R and we got you, right? So, basically, here I want to get the probability of you given how and R. Okay. So what happens is you get an embedding for the specific word how, you get an embedding for the specific word R. So the model identifies this is how, this is R. Then it runs a softmax over all the vocabulary embeddings and it computes conditional probabilities from that and sees based on which embedding is this conditional probability the highest. Then it finds out that based on the embedding, specific vector embedding for word R and specific vector embedding for the word how, you get the specific vector embedding for the word u, which gives the highest probability, or which gives the highest match. So probability here is just match, right? On those matches, we are doing a softmax to convert them into 0 to 1 numbers. It's just the match. So we do an embedding to embedding match. We do a closeness match of the embeddings to get the probabilities. That is one way. The other way is you hard code some probability. That is not a way which is used. Actually, let's not go into that. It is not used. The main way is that you do a vector to vector match and you see which vectors are close. The vectors which are close have a high matching value, and then you can just run a softmax and that gets converted to a high probability, right? That's how we are doing it. We do a semantic match between the embeddings. That is why this embedding, the word
So the
embedding matters.
softmax, the only in the softmax layer, the probability is coming.
Yes,
But
yes.
learning the
Here there is
weights,
no probability. Here just the
learning the
embeddings are
weights
working.
happens for the input layer based on the embeddings.
Yes,
Similar words goes to the same vector line, so
yes.
that the difference has to be minimal, the
Minimal.
length
Yes.
or whatever it is. And then the H naught, how those weights are H naught, the hidden layer weights, how that is getting learnt.
So hidden layer weights, we are doing back propagation, right? We will do the gradient descent and update them with the loss. If this loss becomes high, we will back propagate and we'll update and then we'll
Okay,
do
it
another
is just
semantic
like a
matching.
lookup only. It is just trying to create a lookup based on the
Yes, yes, of the
whatever is
closeness.
your corpus.
Yes, whatever is my corpus. See, one more way is that if you see a corpus, like suppose this is a, like let's go back to the net only because I'm not able to write those many words. Let's come back here. Like suppose if you see in this corpus, like the Indian Premier League. So everywhere the word IPL is coming, this word Indian Premier League is coming. And so you understand that whenever I have the word Premier, before the word Premier I have Indian, and after the word Premier I have League, right? So the match should be high because these words are used together, right? So even on when you train the model with that entire corpus, the model learns what type of matches have to come up and what type of closeness comes up, and gives the higher probability scores for those matches. So if I have a sequence that is Indian Premier, the probability for word league is going to be very high, whereas the probability for the word Indian is going to be very low, right? Because if you see after Indian Premier, the word league is coming every time. That's how by looking up the corpus, by getting trained with the corpus, it understands which word is coming after which word and which word is not coming after which word or which sequence. That's how it actually gets the idea of how to create the embeddings.
So all the LLM models reply is based on this. Not really, it knows the concept of whatever the query or prompt what we are giving. It just goes
Yes, yes,
straight,
it does the
it
semantic matching.
search
Yes,
different websites, take it, and then put this into a corpus, and then try to see the probability of the
then
first.
sees the probability and then it generates the
And
sequence.
it
I mean,
just
the most accurate sequence. Yes, it does not know. Like LLM does not know
doesn't
anything.
know anything what I
Doesn't
asked.
know anything. Yeah, yeah. It just does the semantic matching. So that's why generating the words as embeddings become important, so that we get that sense of matching from the corpus.
Thank you, sir.
Okay. So yeah, we'll actually keep discussing this in the upcoming weeks as well. When that we'll use the more bigger, like the advanced tech models, and that these ideas will even come again. So if the basis, the idea is same, the model does not know anything. We have to just make sure that the embeddings that we learn, those actually play a crucial role, and we have to make sure that the matches are more accurate for the correct words. Yeah, Shubham.
So like after this all the things, can we make our like small GPT version on all in our local machine?
You can, and actually, we'll be doing one exercise in upcoming weeks in which we'll be like giving you some text like in some language, and we'll ask you to train GPT to adapt to that text. It's fine tuning. You have heard about fine tuning in week 4, right?
Yeah.
Where you
Yes.
take the existing model and train it on your data. Something like that we'll be doing soon.
Like from the base, I can create any.
Not from the base. You can create from base, but for that you need very heavy GPU resources for the base. We
How
will
many?
not.
Like I have inbuilt 8 GB.
I'm not sure whether it will be sufficient. It might be, but I think in this we'll not be learning how to create your own model. We'll learn how to adapt the model to specific data, which it is not adapted to.
Okay.
Like I'll tell you one thing: in a degree level DLP course, there was one activity in which we had fine-tuned GPT on 13 Indian languages, which it didn't have any idea about, like Kannada, then Sanskrit, and all these languages, which GPT does not know at all. It was fine-tuned on data on those languages, and then GPT was able to do sentiment analysis, next word prediction on those languages pretty well. So those sort of exercises we'll be trying out in this
So
course as
that's a,
well.
that is the fine tuning. No? That is the fine tuning part.
Fine tuning part. From scratch, you will also be building a model. Like in week 10, you'll be building. That's not going to be a excellent like a GPT mod type of a model, but it will be based on a traditional encoder decoder architecture. We'll be building a model which does that, which is translation. You'll be doing, I think, English to German or something. It does that translation. That we'll be doing in week 10. That will be from end to end, scratch. From scratch, you will create new model. So no fine tuning.
Like it's like I will give some input and it will reply me on that.
Yeah, you will give an input, you will first state the model and then it will reply. Like you give English, you get French. That type of
Okay.
thing you will do. Right? We'll
So
do that
similar
in week
thing
10.
only. Yeah, similar things only.
Yes, we'll be doing fine tuning of GPT at degree level. Yes.
Sir, is
We'll
it
be
latent? So, sir, I was saying, so how is the latent space coming to picture for this RNN?
latent space can be, you can visualize it as the vocabulary and the dimensions in which the vocabulary is existing, the
As
embeddings.
you said, with it'll search for the semantic words and the
Yes,
semantic things,
yes,
but
yes.
same word can be used for different purpose.
Yeah,
That's
that
what
is
I'm.
why I said the attention mechanism is important, right? The same word it first was used for the word dark, right? Then it got used for the word animal. So how do I do semantic similarities there, right? So that is where the RNN fails. So that is why after semantic similarity, we have to do that attention, the attention mechanism, and combining both of them, we get accurate models. That is why if you see RNN is not used anywhere now because RNNs are very limited. Okay, so that is why when we use transformers and GPTs, we use semantic similarity plus we use this concept of attention. Then we get accurate models after that. Okay. So we'll study
Okay.
the limitations of RNN in the next session, and that we will understand. Like I'll give you an idea of what the limitation is. There is no understanding of attention, right? Because it just sees the words one by one, and one after the other. What is the next word to generate? There is no idea of what the word can mean. Same word can mean multiple things in multiple contexts, exactly, right? Which we saw also an example. So that is where we have to combine the next word generation idea with the attention idea, and then we'll get the model which is actually good, adaptable. Okay.
Yes, sir. Right.
Yeah, so in the next week and the week after that, we'll be exploring these concepts much more in detail. This was the introduction week only, so we don't have much here. In the next week onwards, we'll see limitations and then we'll see how those limitations can be solved with more advanced models after that.
So what
Something got
questions you
discussed
practice
about
for the
yesterday's session. What
quiz?
happened in yesterday's session? Like, was it some NPP related?
No,
No,
week
sir.
8
The
yesterday.
theory was discussed by Levin, sir.
Week 8,
Okay,
yeah.
Yes.
They are used and example.
okay, week 8. Okay. So, did you have a session for week 7 before this? Like, sir, did week 8, like this week it will be done, no? Like,
Yes, previous Friday we have week 7 session.
okay, sir took week 7 session. Okay.
Yes, sir.
Okay, then it's good. Then I think this will be a good revision for you today, right? Again, with those concepts. We'll do week 8 also in detail. I'll take an extra session next week and we'll do week 8 as well in detail. Okay.
Okay, sir.
And then we'll have the next Saturday, we'll have the revision session just like we had for quiz 1. Before that, in the weekday, I'll take one session. That will be for week 8. Okay.
Okay, sir. Thank you,
Will
sir.
there be a
I,
mock for quiz 2?
yeah, I think there will be. I'll just confirm with Levin sir, but there should be a one mock, probably. Okay. In case there is no mock, I will share some questions with you, some extra questions for practice in my session. Before my session, I'll share it, and in my session, I'll discuss it. Some extra questions, okay? Like 10, 12 important questions type of thing. I'll make and share it with you.
Okay,
If
sir.
there is a mock,
So,
good. Otherwise, I'll share the PDF from
so
my side.
are we done with today's session?
Yeah, topic wise, that because week 7 was not much, so topic wise we are done. If you have any questions, we can take it up. One announcement for quiz 2, that quiz 2 will contain week 1 to 8. Most like 80% weightage will be for 5 to 8, but some questions will be there from 1 to 4 also. Okay, so it's the like I confirmed with the other instructors, so they said that it is 1 to 8. Okay, so you have to prepare the initial weeks as well.
Okay, sir.
And that is good in the sense because in the end term you have all the weeks, right? So you will get a good recap of 1 to 4 as well. So that'll be good. Because after quiz 2, I think we just have 3 weeks for the end term, like not much time, 3 to 4 weeks. So it's good to have the recap first. Okay.
Okay, sir.
Yeah. So that is it from my side. If you have any other question, we can take it up. Otherwise, we can wrap up for today and we'll meet next week with the week 8. Okay, then. So all the best. We'll meet
Thank
next
you,
week.
sir.
And
Thank you.
yeah, thank you so much. Thanks, everyone.
Thank you, sir.
Good night. Thank you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Thank you. Good night. Yeah, Disha.